Okay, let's go ahead and get started. The time is yours. Please ask any questions. I updated the exams page with the answers to the practice exam. The very first question was strange because there were 2 right answers. So just circle both. But the other questions are here. You have these book problems. It turns out, though, that some of them are area between curves, I think, which isn't on this exam. We're going to cover it on Friday, and it'll be on the final. So today's review and your exam's on Wednesday in class. Please ask any questions. Yes? On page 261, number 57. Is it one of the assigned problems to try for extra? Did I tell you to do it, or did you go do it on your own? Okay, okay. Go to page number one more time. Okay, page 261. Question number 57. It's the L'Hopital's rule section. And it's the limit as x goes to infinity, 1 plus 2x, all raised to 1 over 2 times the natural log of x, if I'm not mistaken. It's too small for me to try to copy and paste, but I'll go into, let me give it a shot anyway. This is the L'Hopital's rules section. It's section 4.5 in our text. It's on page 261, and the question is about number 57. I think it might have had something similar to it on the online homework from that section. Sorry, 1 second here. I have a lot going on. The computer system is slow. Okay, so it's question number 57. Let me blow it up here. Great. 1 plus 2x raised to the 1 over 2 log x. Whenever you give a limit, the first thing you should try to do is to think about what happens as x goes to that number. Now you can't officially plug in infinity, but what you can do is as x gets big, 1 plus 2x is big, the interior is getting large. Now the exponent is 1 over 2 times the natural log of x. So the exponent is getting small. What's happening is this is going towards infinity to the 0 as a power. 1 over 2 times the natural log of x goes to 0 as x goes to infinity. The numerator is constant at 1 while the denominator is getting very large. Okay, great. So it's an indeterminate power. That's a clue as to what you should do. You should let y equal that limit. Take the natural log of both sides. Bring the natural log inside. I'm going to skip some steps if that's okay. And then bring that exponent down in front. it creates a fraction. Let me just go right to what the fraction is in the interest of time. It's the natural log of 1 plus 2x all divided by 2 log x. Hopefully that didn't skip too many steps for you guys, but that's the idea. We need to do this algebra so we can use L'Hopital's rule, and that's where we're at now. We're in the form infinity over infinity now. It's very important that you write these steps out. You write limit out. You write natural log on both sides. If you're going to say this, technically you got to put quotations around it. The way I write it up is the way you should write it up, and if you don't, then you're going to lose credit. If you leave things out, technically what you're doing isn't true. And so we need the limit on each one to the very end. We need the natural log. Yes, you could do all the algebra, but without the formality of the limit, it's not none of those algebra steps are true. And so I saw in some of you who turned in your homework, it was just a bunch of thoughts and then the answer. And that's not going to get you full credit on the exam. The write-up is important. You have to follow the steps and you have to write out the steps. And so it needs to look like this. Now that we have an infinity over infinity form, we can do L'Hopital's rule. Is it getting it to this point that was the trouble, or from this point on? It came from bringing this down. This is 1 over 2 log x times the ln of 1 plus 2x. The step in between, the intermediate step that I skipped. The power of logs allows you to take the log of something to a power and bring the power down in front. Yeah, check our notes on L'Hopital's rule. I have the step-by-step blow on how you should do this. Blow by blow, step-by-step recipe on how you handle indeterminate powers. Yes? So finish this from here. This is undone, but you can finish it. Go ahead.
Can you put number 23 on page
270?
Yes.
Question number 23? Okay, I'll take you through setup. A silo, base not included. It's like the one for the online. A silo, base not included, is going to be constructed where you have basically a hemisphere on top of a cylinder. There's 2 parts to this. Let me take this part first, sorry. Okay. It's important that if you went through and made it through the online homework by using the help me solve this all the time, you want to make sure you can do those problems by yourself without that. And so it's important that you maybe go back and revisit those problems. So here's the rest of the problem. Okay, and we want to take and construct this, have a cost, want cost to be minimized, cost of construction to be minimized. Volume is fixed. They don't give us the fixed volume. I think they did on the online. So let me take you through setup at least. On the exam, I'll give you a fixed volume. I'll give you a number because without that, the whole thing is in terms of that fixed volume, and I'll call it V. But let's say the cost of construction per square unit of surface area is twice as great for the hemisphere as it is for the side wall. So we have a hemisphere and then a side wall, and the cost of construction
per unit of surface area is twice as great for the hemisphere as it is for the sidewall. So the cost of the hemisphere is twice the cost of the sidewall. Does that make sense from that sentence? I'll give you numbers though. This is all in general here. So what happens is everything is with variables involved, but you'll have specific numbers. So the main idea though is that this is the thing that you want to, the volume is fixed, cost of structures to be kept. You want to minimize cost of, so whenever you have a optimization, you want to find the thing that you're trying to minimize or maximize, cost of construction, and cost is made up of the cost per square foot times the square feet. Okay, and there's different parts. There's the part for the hemisphere, and then also the part for the sidewall. So you can't just take the cost part, you also have to involve the area. Cost per square foot times square foot. Sorry if I switch my units, the way I'm writing my units here. Okay, assuming that the units they don't even give you any units, so we're just assuming that it's in square feet, that's fine. So that would give you cost. You want to minimize cost. So the hemisphere, we're talking about the area, the surface area. This square feet is surface area. And there's a formula. Hopefully you have room on your cheat sheet for formulas, because you don't want to get a problem wrong because you don't have the formula. Surface area of a sphere, surface area of a whole sphere, 4 pi r squared. And so half is a hemisphere would be 2 pi r squared. That'll be the surface area. And then times some given cost. Here we're going to have to say it's twice the sidewall cost. Let me just, to make things easier, let's say the sidewall cost. It's just some number. Sidewall cost is $6, say. It's unrealistic. Let's go with that. So then the cost of the hemisphere then will be twice that, $12. The cost of the sidewall would be $6. And then the surface area for the sidewall, what happens is if you have a cylinder, you slice it and unroll it, and what you have is a rectangle. And so the area for the sidewall is a rectangle. When you unroll it, the length of it is the circumference, 2 pi r, and the height of it, the cylinder is the height of that rectangle. And so you just end up with 2 pi r for the area of the lateral sidewall. Okay, and that's making up your cost function. And then there'll be some fixed volume, 2 pi r h. So there'll be some fixed volume, pi r squared h, plus the volume of the dome part. The volume of a sphere is 4/3 pi r cubed. These are things that come out of nowhere on you. Hopefully they'll be on your cheat sheet. Pi r cubed. So half of that will be 2/3 pi r cubed. And the whole point is this is supposed to get you. This is multivariable, and then this constraint here, which you'll be given some known volume. You'll be given a number here, is to help you solve for one of the variables. So most cases here we're going to be solving for h, and then we can replace h in here and have a variable r only for cost, and will be single variable. So this is your constraint. That volume is fixed. Okay, I'll stop there. This is 2 in general. This number 23. There's too many things left up for variables, and so I wouldn't have you solve exactly 23. But the one you had on the online, I think had numbers in it, or maybe not. I think so. Okay, is that good enough?
No, wait. I'm just wondering, 2/3 pi r.
Where did 2/3 pi r cubed come from? The volume of a sphere is 4/3 pi r cubed. So for these things, I have to take half of them for my hemisphere. Any other questions about this one before we move on? Yeah. I just made it up. I mean, this thing just had a generically, whatever this cost, this guy is double. So I had to make up a number. I just made it up. Okay. Any about this one? Okay, 1 second. Yeah, go ahead. Yeah, we're ready to move on. Go ahead.
Number 19.
Give me next. Number 19 on Page 270. I'll take you through the setup again. It's similar to the one that was on the homework. Yeah. I wrote a bunch of stuff. I guess I didn't keep it. That's okay. Sorry about that. Anyway, I'll take you through the setup. I think it's necessary to have a picture. So on the when it was given on that exam, whichever exam it was given, they gave a nice picture. The picture was very helpful. Let me do it for you here. If you're going to inscribe a cylinder inside of a sphere, a certain kind of way that would happen. Hopefully this doesn't obscure anything. But anyway, here's my sphere, and then my cylinder will be put in such a way that they'll share the center of the sphere will be like the sort of geographical or center of mass, kind of, if everything was equally distributed, of the cylinder. And it's very important to draw a triangle. Let's draw this triangle here. If I go from the center of the sphere out to this bottom corner here, intersection between the sphere and the cylinder, I know the radius of that sphere is 10, so that's my hypotenuse. And then the radius of the cylinder, however, is not 10. The radius of the cylinder would be this distance down here, which we'll call x. And then in this right triangle, let me go ahead and finish drawing the right triangle. I'm sorry, I should change the color or something. There's a right triangle here. And it's 10, so let's just say yx and 10. Yx and 10. Now, the height of the cylinder, by the way we're going to use symmetry, we'd have to say that the height of the cylinder is twice y, and the radius of the cylinder is x. So if you want me to maximize the volume of the cylinder, if you want me to maximize that, I'll start off with the pi r squared h, but I want to put in terms of x and y, replacing h with 2y, replacing x, replacing r with x. So I get this formula here that I want to maximize. It's multivariable. Okay, so I need somehow to get a relationship between x and y. I go to Pythagorean Theorem that says that x squared plus y squared is 100 in that right triangle there. And so it's best if I just solve for x squared, have it as 100 minus y squared. And then sub that in, and you're on your way. Now it's single variable, and you're on your way. Go solve it, and make sure at the end that you prove that you've maximized. Okay. Okay, now you're. Yeah. Homework 9. Spring 2011. we have this area accumulating function, g of x. We don't actually integrate the function at all. We're asking for the derivative of that function. Fundamental theorem of calculus says that we just take and replace the dummy variable t with the function in x that's in an upper limit. I'm screaming because I'm trying to over talk people. I don't know how much longer I can keep it up. So replace the t with the 6x. But since 6x is more than just the 6, you have to use the chain rule and multiply by the derivative of 6x. It's fundamental theorem of calculus, officially part 1 it's called. And then plug in 1 over pi to that. You put the entire function replacing all t's, and then you do the chain rule. Solid. You can finish on your own?
Yeah, but so
okay.
No matter what is going on with the x, it's just x or 6x or x squared, you just say.
Okay. That's it. Fundamental theorem of calculus part 1. Questions about this one before we move to another? Okay, go ahead. Yeah. Yeah, that's good. From homework 9? What do you suggest? How do you solve it? Yeah.
Make it 1 over the denominator first and then times dx. It'll make it look better.
Say it one more time. Sorry, I missed it.
Like reformat it first, do 1 over the denominator and then times dx.
Okay. So you're saying
Put it in an easier format to work with.
that x is going to be there too. I don't think that's going to. Yeah. First you should do a u sub and then do that. That's what you need. But first you need a u sub because if you involve the x being to the negative first power, it's going to be trouble. Isn't this what? It kind of looks like arc sine. You'll see that in 1 second. This x though kind of messes that up. So we have u is log x, du is 1 over x. So we don't have to do it as an arc sine. In fact, that x doesn't makes it so that we can't do arc sine. And so we end up with 1 minus u squared underneath a root, replacing the root, and then the 1 over x dx gets replaced with du. So now it's exactly like an arc sine. 1 over 1 plus 1 over 1 minus u squared in a root like this is the antiderivative of it is arc sine. So we transform back and we put in that we have the arc sine of the natural log of x. Okay. So it was our job to find it in terms of x. This little side work was to help us find that antiderivative. We trade it back in for x. We plug in e. We plug in e to the half, and then we plug a 1 in. I wrote it, instead of writing it Rudy, I wrote it as e to the half, so you can see what happens as you plug that in. If you have the ln of e to the half, the ln e cancel and you talk about the arcsine of a half. The ln of 1 is 0, so from that you're going to subtract the arcsine of 0. And then you just see all the work. Okay. So you have to know how to evaluate the arcsine function. That's all old material now showing up on this exam. I'll let you finish it from there. Yeah, go ahead. Now, go back and study the arcsine notes. The domain of arcsine, or I'm sorry, the range, the angles that come out of it are from minus pi over 2 to pi over 2. Yes?
Could you number 93 on page 356?
Give me that. Give me that. Okay. Ah. Too much going on. What number again?
93.
On page 356?
Yeah.
Just give me 1 second, sorry. Too much calculus for this computer. $356.
Yeah. 93.
What are you going to let u equal? Suggestion is to make it everything that's underneath the root. Let's try it. If I let u be the entirety of 1 plus 3 sine squared x, I take its derivative and I get 3. I treat this like sine x whole thing squared, so I bring the 2 down from the power rule. I take sine x officially to the first power, and then I multiply by the derivative of sine x, which is cosine x. We're good because we have 6 sine x cosine x. Why is that good? The rest of what I have to sub for is 3 sine x cosine x. So I just divide by 2. And I have how I'm going to sub for 3 sine x cosine x. I'm going to do it by taking half of du. The root now has a u underneath it. It's in the denominator. And all of the numerator is replaced with half of du. I'm going to rewrite that as u to the negative 1/2 and use the power rule in reverse. Add 1, divide by the same thing. So I have u to the half. Instead of dividing by a half, well, let me go ahead and write this divide by half. Because this half out here and that half from integration conveniently canceled. I want you to think about all of this as side work. Necessary. I need to see it, though, for you to tell me that the antiderivative of the original is just the square root of 1 plus 3 sine squared. And you go and evaluate it from 0 to pi over 2. Yes?
How did it canceling out a half or half?
I had a half that came from my u sub and a half that came from my integration. Those two guys right here, this half from my u sub and this half from my integration cancel each other out. Yes. Are we done with this one? Any other questions about this one? Okay, you're up next.
Question 75 on page 2.
And then you're next. $270? What part are you having trouble with? Showing that L squared is 2x squared over 2x minus 8.5? The original paper is 8.5 by 11. And you're going to fold it. And we're going to have a right triangle. And it's our job to show that L squared is 2x squared, 2x cubed over. So on an exam, I wouldn't give this to you, but we could do it though. But what you should take away from this problem is the thing that we had on the notes. Notice that they're interested in minimizing, minimizing L But notice what they do. They instead look at L squared, because however you get this formula, it involves a square root. L squared is equal to this. And so if you're interested in minimizing or maximizing a formula that has a root in it, you can minimize or maximize what's underneath first. And that's what they have you doing. They say, well, here's this formula. I could spend time talking about where it comes from, but the thing I want you to take out of this, though, is that my formula, the thing that I'm trying to minimize, ultimately, L, has a root of all of that. But instead, to make my life easier, I'm going to minimize what's underneath. It's equivalent. Minimizing what's underneath the square root will be the same thing as minimizing the square root. And so that's what they take you through here. I don't think it's worth our time to show you where this comes from. Maybe after class or something I can show it to you. Okay. All right, you're up.
Number 5 from the practice internal unit.
Okay, it became late. The answers are on the page now. Just refresh it. We have number 5 is a. Sorry. Yeah, number 5 is an oh, that's 3. Sorry. Number 5 is a find the area, or first estimate the area using rectangles, and then find the exact area, the actual area, and see how much more the estimate is, how much larger it is over the actual area. So was it the actual area that gave you trouble, or the estimation that gave you trouble?
I got F, and it said the answer was B, so I don't know why I didn't know.
Okay, well, if the majority got F, it could be a mistake on my part. The actual area, what'd you get for that?
42 and 2/3.
42 and 2/3, and the approximation?
I got 150 over 3.
150 over 3?
Yeah, it's
50?
Yeah.
Are we in agreement? Did you use left endpoint or right endpoint? You used left endpoint, and you got 50? Okay, so 50 minus the 42 1/3 is the 22 over 3. We'll go with that. So we're saying that I said the answer was B, but the majority of people are saying that the answer is F. Okay. But it's the execution that I want to make sure we take away from this. If you're having trouble with the execution, we should talk about it now. Yes? Not about this one? Anyone like to see the execution of this one? Which part? The approximation? The actual was just a straightforward integral. Let me talk you through the approximation. So we're talking about taking 0 to 4 and cutting that interval into 4 subintervals. And on each of those subintervals, using the left endpoint. So we have the interval from 0 to 4. Cut it in half again. Conveniently, that's on integers. So I use 0 to 1, 1 to 2, 2 to 3, and 3 to 4. What I do is I go up and evaluate the function at the left endpoint each time. So I evaluate the function at 0, I evaluate the function at 1, I evaluate the function at 2, I evaluate the function at 3. Those are all the left endpoints. Each time, the width of the rectangle is going to come from the difference between these, which is 1, so I'll just pull that out. And so what's the function at 0? 16 minus 0? 16, 16 minus 1, 15, 16 minus 4, 12, 16 minus 9, 16 minus 9 is 7. Add these up. The approximation error area will be that sum. Okay. So I think you'll get 16/3 if you put a 5 here. That's a mistake that was made. Anyway, we get what's that? 31 and 19, exactly 50. Okay, and you can take it from there. So we have time for only a couple more. Jack, you're up. Two. Okay, I'll take you quickly through it. Yeah, this is also the practice exam. Number 2. X goes towards E, so natural log of E is 1. X minus E is 0, so 1 over 0 gets very large. And so this is of the form 1 to the infinity. Indeterminate power again. Let y equal that. Take the natural log. Bring the natural log in. You're dealing with the limit as x goes to e, technically from the right-hand side of the natural log, which allows you to take this exponent and bring it down out front, creating a fraction. The fraction is the log of log x divided by x minus e. The point is that now it's in the format of 0 over 0. Log of e is 1, natural log of 1 is 0, and e minus e is 0. So you use L'Hopital's rule, and maybe from here on is where the problem is, or was it that far? That far is fine. Yeah, it's the derivative here is 1 over the entire function. Then you multiply by the derivative of that entire function on it, so you get that. And the denominator derivative is just a 1. And you're on your way. You'll get it. But remember, that's not the final answer. Don't circle F. You have to do H. You have to do E to both sides. I'll let you finish that out. Let's try to fit one more in. Yes? That's for an indeterminate product. The way we have it set up, convenient. Usually when you bring it down, you might have a product, but the way this thing is a fraction, when you bring it down, it creates your fraction for you, so you don't need that to create the fraction. Yes? What number? X squared times the natural log of x. This is one of those where you have f times 1 over g. Whoever just asked that. 63 is x squared times the natural log of x. X squared is going towards 0 as x goes towards 0, but natural log of x is diving off towards negative infinity. And so we have these two competing against each other, and that becomes an indeterminate product. 0 times negative infinity is not necessarily 0 or negative infinity. This is an indeterminate product. It's very important you recognize what type it is, because that's going to give you your recipe on what you should do. It's an indeterminate product. I have them on the notes laid out to you exactly what type it is and then what to do. I'll give you the steps. What do you do for an indeterminate product? You create a fraction by doing this g times f, making it f times 1 over g. Easiest part is this reciprocal, the reciprocal of this polynomial part. So you create a fraction by calling it log x times 1 over x squared. Now you have a fraction. And that fraction is going to infinity over infinity. Technically negative infinity over infinity. Now you can use L'Hopital's rule, and you're on your way. Go further or no? The person who asked this question, go further or no? Yeah, it's about recognition. A lot of things on the test is you got to recognize where you're at and then know what to do once you're there. If you never recognize this as an indeterminate product from the beginning, your wheels are spinning, but you can't get anywhere. Okay? It's only 1 more minute. I really don't have time for another. You can catch me in office hours. Please go to recitation. Although you don't have a quiz, it's a good place to do some review. If you're Thursday, go to Tuesday.
I had one more question about the practice exam.
Good.
Okay, so for number 3, I think it was. So I took the first. It asked me to integrate. Basically integrate it twice.
Yeah.
So I did it the first time.
Yep.
I took the derivative. I took the integral, and
Yeah.
I got this. And
Okay.
I think it's right.
Looks good. Okay.
And so I went through the steps. I think I did the steps correctly. But I got 128. So I got G.
Yeah.
The answer was something else.
No, it should be 128. I don't know what I said it was. G. So number 3 is G.
Yeah.
I said it was something different.
I think so.
3 is G.
So when you get from here, can you just take the derivative of the top and the bottom would be negative 0?
That might be it. Let's see.
X over negative 2.
Okay, that sounds good. So then, yeah, you're on your way. You're on your way. Okay. I'd like you to put some limits in there. I need you to tell me that you've done L'Hopital's rule. But that's it though. That's it.
And then can you plug in 0 here?
No, don't do it. Simplify first.
Do we have section 7.1?
Yeah, that's the E and log stuff.
Okay, so
Take a look at it. You'll see. Yeah, open your book up. It's good. You should use it.
So I've been meaning to sign a lease for a house today, so I can't come after class.
Okay.
But just finishing out this one. When you have to like change this into U, but I guess you did this instead. What did this come?
It's from here. Root E is E to the half.
Yeah. Why are you using it to that?
Because these are the limits of integration. After you find the antiderivative, you got to plug in the limits of integration. So this is me announcing that I'm about to plug in the. This isn't me raising it. This is me saying, okay, now I'm about to plug a E to the half in, then I'm going to plug a 1 in.
Okay.
So this is like an announcement kind of. This isn't an actual raise to that thing or nothing like that.
In the last problem we did, you had ln of 0.
It's
Why
not
is that
undefined.
infinity?
It's just a graph. The graph of ln dies off through. I thought ln of 0 was undefined.
Don't
Not
go
undefined.
through it.
The ln of anything over here is undefined, but ln of 0, as you approach 0 from a positive side, goes to
And
negative
you'll-
infinity.
okay, same thing with 1 over 0, that's why it's close to infinity as well.
The one before that, you had 1 over E minus, or X
As long as it's a plus sign, you know what I mean? Like,
Oh, okay.
then it can dive off.
It's from there, okay.
Or get big. You know,
Yeah.
1 over x looks like this. So as long as there's a plus sign, you can shoot off to infinity.
Oh, gotcha.
Yeah.
Okay.
Alright, thank you.
Yeah. You're my.
How did you know that this was U? Like, just the ln of x? Like, I thought it would be like anything else.
You can try it. Try it. Look, try it. Try the whole thing as you.
Okay.
And you'll get something very bad.
Yeah.
Try it out.
Okay, and then like, okay. So always just kind of test it out.
I would have chosen to think of the whole thing.
Yeah.
My first thought would have been, let's do the whole thing.
Okay.
But you'll see, as soon as
always,
you
like,
go to
you're
take the
trying layer it,
derivative-
and then like when you start taking it, it doesn't make sense, and then you do
Yeah,
another
yeah.
way.
It's all about the rest of this showing up as the derivative,
Okay.
and it won't if you use the whole thing.
Okay. All right. Thank you.
Hey.
What is it up until like substitution rate?
Like everything up until substitution.
Yeah, there's a list here. Yeah, the 7-1 is not new. It's the e's and logs mixed in. So we've been doing everything we've been doing with e's and logs in it. That's what 7-1 is.
Okay, and not the area between the curves. Okay.
Not area between curves.
Okay, thank you.
Okay, yeah. Okay, I'll meet you up there.
Yeah.
Okay, all right, sounds good. So my time today is I have class at 12, so 11 to 12, 1 to 2, and then I come back and I'm in my office from 4:15, 4:30 to 6.
Okay. Finish class at 2, and then I have practice at 4. So should I come kind of like 5:15? Yeah.
I mean, I'll be there.
Yeah.
Yeah.
Okay.
If I'm not there, there'll be a note saying where I'm at.
All right.
Okay, so basically, oh yeah, LN0. How is it? Okay, if it's negative, can we just make that negative?
It's just it's just because of what ln does. It goes towards negative infinity as x approaches 0 from the positive side.
So like when we do like, it's negative, right? So like we do like x squared over negative ln x or something. You said this is
I said you just flip this guy.
And oh yeah, and the one that they said that there might be a mistake on, is it true? In the end? I didn't catch that. It was the 4 endpoint rectangle one.
Oh yeah, what's that? What's that one called? Number 5. Okay, I said it's B, but apparently it's F. So I'm gonna change the website to say that 5 is F.
Okay.
I'll do that. I'll change that. I can't do it right now, but I'll do it.
Yeah. And then this one that we did, which is like one of the first ones we did. I don't know if you remember, but did you finish your problem or?
There's a lot I didn't finish. Let's see here. That one I got a good start on it though.
Okay. So is that what you? Okay.
That's as far as I took it.
All right.
Okay. Sounds
Thanks
good.
so much.
Yeah.
Have a good
All right.
weekend.
Keep working hard. Have a weekend again?
Yeah.
I wish it was.
I'll be back.